Hey guys, this lesson is going to be covering rational functions, their asymptotes, and graphs. So before we really begin our discovery of rational functions, I want to just kind of go over where they arise. Okay, so here's an example. Let's say that the Seward High Travel Club is going to Spain in the spring, and it costs $450 for each of the students' airline ticket, but then another $2,000 for additional costs. That additional cost can be offset by the more students that go, the cheaper that becomes because they're going to split that $2,000 by all the number of students. Everybody has to pay the 450. The 2,000 is going to get split. So if we let x equal the number of students, let's look at how we could write a function to represent the total average cost per student. So one thing that we know that each student has to pay $450. So I'm going to say the cost, and the cost is going to be dependent on the number of students, x. So if x is our number of students, the cost depends on that. So our function, I'm going to call it c of x, for c for cost and x for the number of students. Everybody has to pay that $450, so that's part of the cost. But then the $2,000 is going to be divided by the number of students who go on the trip. And that $2,000 would be for things like the chaperones and their hotel perhaps, or other things, travel to get to the airport and things like that. All right, so the $2,000 is going to be split by x students, or divided by is another way to say that, by however many students go. So if you think about it, like if one student goes, just one student, they have to pay that, x would be 1, and you'd have 450 plus 2,000 divided by 1. The cost would be $2,450 for that student. If two students go, well, they split the $2,000, so they each pay $1,000. Now the cost has gone down dramatically to $1,450. And if there's a lot of students who go, the price is going to start getting closer and closer to that $450 mark, because each person is going to pay a smaller and smaller fraction of that $2,000. So hopefully that makes sense. But this right here is a rational function. And what makes it a rational function is that we are dividing by the x instead of like multiplying. If we were multiplying by x, we would have a polynomial function. So here's an example of a rational function. And if we look at, like, if we graph this thing, we have an asymptote. My asymptote is a guide for the graph. The cost of this trip, and I'm only graphing this because it's an applied problem, I'm only graphing it in the first quadrant. And so let's say I'm going to go by like 5,000 here, or 500 I mean. So 2,000, 2,500. So this is the cost in dollars. And then as the number of students goes, and notice that I'm not going by the same scale on the x-axis as the y. Always pay attention to the scale. Okay, so here's how this works. One student goes on the trip. Hang on here. That one student pays $2,450, so somewhere up here. And in this applied situation, this is called a discrete graph because we're just plotting points. We're not connecting them because we don't have half of a student. So, but normally when we're graphing rational functions, it'll be a continuous graph. Two people go, they end up paying so f of 2, if I evaluate f of 2, you're going to divide that 2,000 by 2 of you, and you end up with, this is 1,000 plus 450, so f of 2 drops the cost per person to $1,450. So about here. 3 people go, it's still going to drop, but not by as much, but 2,000 divided by 3 plus the 450 is $1,116. So 3 people go, it drops a little bit more, but not as drastic of a drop as it was here. And then as you go with 4 people, that 2,000 gets split by 4. You each pay, you're going to each pay 500 plus 450, so close to 1,000. A little bit under $1,000. Oops, let me get over here. And then we could keep going for 5 people, 6 people, but eventually, if we had, like, let's say 100 people win, you would take that 2,000, you would divide it by 100. Each person only pays a small fraction of that 2,000. They pay $20, so they'd pay $470. If 1,000 people went, I know we don't have that many students in our school, but let's just kind of pretend that cost is going to approach $450. So that's about maybe right here. That the cost for students is going to start getting closer and closer and closer to this line. And as you go out, it's going to approach that line. And in this case, it doesn't ever reach that line because you'll always have to pay a little bit more than the 450. But eventually, it would just be like pennies if you had enough people. Yeah, if you end up taking 1,000 people, like I suggested, then you'd each have to pay $2 of that 2,000, so it'd be $457. So it's going to get closer and closer to that. That's called a horizontal asymptote for the rational function. And so let's go back to the notes here. So rational functions can be written in the form n of x over d of x. I'm using, instead of f of x, and a lot of times we use g of x, the book uses n of x and d of x, so that's why I'm using that, but both of those are going to be polynomials, which we covered previously, and d of x cannot equal 0 because you can't divide by 0. So some characteristics of the parent function of rational functions, which is 1 over x. It's the most simple graph. And when we had our example, we had 2,000 over x plus 450. The 2,000 and the 450 are transformations of that parent function. It's multiplied by 2,000, which, just a quick reminder, that would be a vertical stretch of factor 2,000. And then the 450 shifts the whole graph up 450 units. All right, so let's look at the parent function. And what we're going to do here is we're going to make a table, but we're also going to use some logic and reasoning to figure out how this graph works. Okay, so if I try to plug in 0, if I want to find f of 0, I get 1 over 0. Cannot do it. You cannot divide by 0. So we have a fraction with x in the denominator. The denominator would be 0 when x is 0. So our domain is from negative infinity to 0, not including 0, with a union 0 to infinity, because the only number we cannot have, the only value of x that doesn't work in this function is x equals 0. And so it would look like that. Okay, and that's because we cannot divide by 0. So let's try another number here. Like, let's say when x is 1, well, f of 1 would be 1 divided by 1, which is 1. So 1 comma 1 would be on my graph. Before I continue, the fact that x cannot be 0 means that we have a vertical asymptote. So in that last function, we had a horizontal asymptote. In this case, we have a vertical asymptote. You're going to see there's also a horizontal. We'll get to that in a minute. All right, so we have this vertical asymptote. X can be really, really close to 0 on the positive side or the negative side, but it can't equal 0. So it's going to be a guide for us. So, okay, so if x is 1, f of x is 1. Let's do a few other numbers here. and then I'm going to go with fractions. I want you guys to calculate what f of x is, and then come on back. Okay, so when you put in 2 for x, you should get 1/2, and when I put in 3, I get 1/3, and when I put in 4, I'm going to get a smaller and smaller fraction as I go out, but it's never going to ever equal 0, because for a fraction to equal 0, the numerator has to equal 0, but our function has a 1 in the numerator, so it will never equal 0. This is going to approach 0 as we go out towards x. When x approaches infinity, the y-coordinates get closer and closer to 0, but they never reach it. So we also have a horizontal asymptote through y equals 0. The equation of that line is y equals 0. The equation of our vertical asymptote is x equals 0, and this asymptote is y equals 0. So horizontal lines are in the form y equals their y-intercept, which is 0, and vertical lines are x equals. Okay, so let's go through this range. So the x, let me finish graphing it first. As we go to closer and closer to 0, so like if I put in 1/2 here, we have 1 divided by 1/2. You flip and multiply, and you end up with 2. So when x is 1/2, this is 2. When x is 1/3, it's going to end up being 3. And when x is 1/4, it's 4. And the bigger the fraction, it actually blows up towards positive infinity, and it's going to approach this vertical asymptote, but it never, ever, x can never equal 0, so it's getting closer and closer, and it's getting to be a bigger and bigger result. If you take 1 and you divide it by like 1 over 100, it becomes, you flip this bottom one and multiply, you'll get 100. If it was 1 over 1,000, so 1/1000th, if x is 1/1000th, it's a very tiny fraction, it's going to approach infinity. Okay, and this function is an odd function, so you could make a table of ordered pairs, but basically we know that if it's an odd function, we know that it's symmetric about the origin, so the other side of the graph is going to look like this. It's going to approach the vertical asymptote, but it's going to go towards negative infinity, and because we'd have negative x values, and so make all these y values negative, and as x goes towards negative infinity, the y values approach 0, but from below, whereas this one was from above. Okay, so it never equals 0, so our range, the y values never equal 0, so our range is also negative infinity to 0, and then 0 to infinity, not including 0. X-intercepts, trick question, there are none. It never crosses the x-axis, it never crosses the y-axis. This function is always, if you think of being on a sled, you're always going downhill. It is always decreasing on, so it's decreasing on negative infinity to 0, because 0 is not included, and then again from 0 to infinity. There are no relative minimums or maximums. We just talked about it. The function is odd. And then we have our vertical asymptote, which is x equals 0. You can fill this in if you want. And then the horizontal asymptote is y equals 0. We will stop there, and we will talk about transformations in the next video.